Hello, my name is Sheridan, and this is going to be an introduction to basic AC analog circuitry. AC, DC, pretty much everything about analog circuitry. We'll get into some digital as well, but not very advanced digital, hopefully. So, in this video I will cover basic math and the kind of software that I use for simulating circuits, which has taught me way more than any college lecture has ever taught me, ever. So, let's get started. This is the software that I use. It's called Falstad Circuit Simulator. It's a really simple applet, and everything is animated, and there are many great things and praises that I have to say for this software. It's completely free. It requires no downloads. You can download the applet if you want to, but in order to use it, you don't have to sign up for anything. It's just you log on to the website, and there it is. Boom. You don't have to give them your email, your phone number, your credit card. And as you can see, everything in the circuit is animated. You can see the current moving, you can see the voltage going up and down on sections of the wire. You can read any component in the scope down below. The only thing that I don't like about the circuitry is that the more components you have on your screen trying to run at once, the slower it has to go. So if you try to simulate all the components in I don't know, a 16-bit RAM, you might run into some slowdowns, or maybe 32-bit RAM. If you were to construct that in the simulator, you may have some speed problems. But other than that, for simulating basic analog circuitry, there's nothing better. I've tried other software, Spice. I don't even remember. Spice is the only one I remember, and it just doesn't compare. It's also great for just simply drawing out diagrams. You can change the settings so that you can make everything black and white, so you can make it printable. So you can see for yourself. All you have to do is go to falstad.com/circuits. When you get there, you will be given a smaller window of operation. There's a link down below on the page where you can click on to get the full screen version that I have here. It's just a different web page. So you can follow along in Falstad if you want to, or you can just simply watch the video. So I'll just be covering the basic math of all circuitry. The great thing about Falstad is you don't actually have to know the math by heart in order to use it. You can simply just tweak your components until you get the right frequencies, the right current, the right voltage. You can tweak everything. Everything is editable. So, basics. Ohm's law. So I'm going to cover the two basic math formulas that pretty much govern all of electrical components. This is how you calculate how much power you use, how much current's running. And if you don't like math, don't worry. The formulas are simple. They have a mnemonic device. Let me show you. So, the other great thing about Falstad is that it has hotkeys. So if you want to put in a text box, you simply press the T button, and bam, text box. Text box appears. Right click, edit, blah blah. So there's two basic formulas, and they go a little like this. Voltage equals current times resistance. So let's take a look at what that means. So here we have 5 volts and 0 volts. This is the ground symbol. It means the exact same thing as 0 volts. So in a battery, the positive would be connected here, the negative would be connected here. Circuit designers prefer to use this symbol for 0 volts as opposed to just connecting it to the other side of the battery, because it's a lot less ink on the paper, a lot less lines to figure out. It's a lot less like a maze and more like a diagram. So let's take a look at what that means. So in this circuit we have, don't get confused here, a lot of beginners make this mistake. When they first see a circuit and it has 2 branches, they think, oh, there's 2.5 volts here, 2.5 here. No, that's wrong. There are 5 volts on both of these resistors. Every single point in this section of the wire will measure 5 volts everywhere. I'll even prove it. We can even edit the wire, show the voltage on the wire. Right? It's still 5 volts there, and still 5 volts there. So we have 5 volts across each of these resistors. Now, as you can see, the yellow dots, which represent current, are flowing faster through one of them and flowing slower through one of them. That's because this resistor is higher. Sorry. This resistor is higher, so the current is encountering more resistance. The electrons are being pushed back harder on this side than they are on this side. So more electrons will flow through this branch than they will through that one. As you can see, we have 50 milliamps over here and 5 milliamps over here. Amps, you can think of amps as as analogous to the amount of water that's flowing through a pipe. So here we have a lot of water flowing at high rate, and here we have a little bit of water flowing at a low rate. So back to our math problem, our math formula here, VEER. So units in electronics, they follow the scientific notation. You have milliamps, megaamps, kilowatts, megajoules. So milliamps simply means there's a point, this is 0.05 amps. So 5 volts, let's see, current times resistance. We have 50 milliamps and 100 ohms. So 0.05 times 100 equals 5. Makes sense. And if we mouse over this resistor in the simulator, we can, if you look down at the bottom right, it'll tell you what it is, how much current's running through it, how much voltage it has, the resistance that you set it for, and the power it's consuming. So you don't actually need to do the math when you use the simulator. It's all done for you. As you can see in the bottom right corner, I means current, 50 milliamps, and we also have 50 milliamps through this wire. So everything on this branch is getting 50 milliamps. Everything on this branch is getting 5. When you have a single line and no forks, it's the same current throughout the line. The other formula that you will need to know is power equals current times voltage. P equals IV. VER and PIV. Those are the two formulas that you need to know that will tell you all of the factors of your circuit. So let's take a look at this resistor. It's getting 5 volts if you look down at the bottom right corner, it's getting 5 volts across it and 5 milliamps. So 5 milliamps times 5 volts is 25 milliwatts. On this side, we have 50 milliamps times 5 volts is 250 milliwatts. So some of the other basic math is equivalent resistance. Let me also demonstrate for you. So let's say we make this 500 ohms. So 10 or 0.01 times 500 equals 5. And 5 times 0.01 is 50 milliwatts. Now you notice as I move the resistance from 100 to 500, our milliamps went down. That's because as you raise the resistance, in order to equal the voltage, the current has to drop in order to maintain the voltage. Voltage is always a fixed point. That differs from power, which is usually your voltage is a constant and your resistance is your input, and so you're trying to calculate equivalent current. Current is a variable, is your variable. Resistance and voltage are usually your constants in a circuit. When it comes to power, your current and voltage are the constants, and your power is what you're trying to calculate, is your dependent variable. So let's talk about series and parallel. So let's build a circuit here. So this is what we call a series circuit. Let's put a voltage source. Voltage source. So these resistors can mathematically be combined into one resistor, and the way we do that is by adding them together. So the equivalent resistance of all of those resistors is R plus R plus R. Equals resistance equivalent. So 1K plus 1K plus 1K is 3K. This is basic math. And so in order to calculate the current running through all of these resistors, you'd simply divide 5 by 3000. Now parallel, this is probably the most complicated math you will need to know for doing the math, the circuitry math, and that is parallel resistance. We're going to build a parallel circuit here. So in a parallel circuit you have two distinct sides, the top of the resistors and the bottom of the resistors. They're all one common point. Copy. So to mathematically combine these resistors, the formula looks like this. R to the -1 plus R to the -1 plus R to the -1. Sorry. Equals the equivalent resistance to the -1. This is how you mathematically combine resistors in parallel. So if you wanted to calculate the current, you'd simply put a resistor that's equivalent to all of these combined into one. That is to say, the current coming out of this 5-volt node. What I usually do when I'm calculating it is I put these parentheses in my calculator and then put this -1 on the on the side with all of my resistances, so I can get here. I'll show you. I simply put the -1 power over here instead of over here. So a couple things to note about, I'll cover that in another video. So yes, this is the basic math that electronic circuitry is based on. There are a couple of other formulas that have to do with specific components, but these apply to pretty much every single component.